Hi folks, this is Linear Algebra Take Home 5. We're given a function from the 2x2 matrices to themselves. And what we're doing is we're taking each matrix, we're taking it minus its transpose. So our first objective is to show that T is linear. So what's it mean for T to be linear? It means given two fixed but arbitrary vectors in V and two fixed but arbitrary real numbers, T of alpha V plus beta W is the same as alpha T of V plus beta T of W. In other words, T respects or T preserves linear combinations. So in this case, the vectors are 2x2 matrices. So I'm going to let A and B be fixed but generic 2x2 matrices. And I'm going to let alpha and beta be two fixed but arbitrary real numbers. I'm going to compute T of alpha A plus beta B. So, by definition, T of a matrix is that matrix minus its transpose. I'm going to use properties of transpose here on this last quantity. Transpose of a sum is the sum of the transpose. The transpose respects scalar multiplication. And now I distribute through the negative, and I get alpha A plus beta B minus alpha A transpose minus beta B transpose. So that's T of alpha A plus beta B. Now, I need to compare that with alpha T of A plus beta T of B. So let's look at alpha T of A plus beta T of B. Alpha times T of A is that, plus beta times T of B. Distribute through the scalar multiple. And rearrange the terms. And there it is. So we've shown that T respects linear combinations. That means, by definition, T is linear. So that'll do it for part A. All right, in part B, we're asked to find a matrix representation for T using the standard order basis. Okay, I'm going to call this standard order basis X. And so what I'm going to do is, as we mentioned in class, there are infinitely many matrix representations for any given linear transformation, from a finite dimensional vector space to another finite dimensional vector space. So what I'm going to do is I'm just going to find the matrix representation with this as the basis for both the domain V and the codomain, which is also V. Let's remind ourselves what matrices comprise X. E11 is the matrix that has 1 in the 1, 1 position and 0 everywhere else. E12 is the matrix that has a 1 in the 1, 2 position and zeros everywhere else. E21 is the matrix that has a 1 in the 1, 2 position and zeros everywhere else. And E22, well, that's the matrix with a 1 in the 2, 2 position and zeros everywhere else. All right, so that's my ordered basis X. So I'm going to use I'm going to find the matrix. I'm going to call it M from X to X. And how do I do that? Well, what do? I take in each column, I take T of each of these basis vectors, and then express that in x coordinates. So this will be t of E11 x coordinates, t of E12 x coordinates, t of E21 x coordinates, t of E22 x coordinates. So let's start going through and find each of these. So t of E11 is t of the matrix 1, 0, 0, 0. By definition, I take that matrix minus its transpose. Now, this is a symmetric matrix, so its transpose is just itself. So when you do that subtraction, you just get the zero matrix. So what is this in x coordinates? Well, this is my ordered basis. So I look here. In the 1, 1 entry, I have 0. So that's 0 of those. I've got a 0 here. That means there's 0 of those. I've got a 0 here, 0 of those. And finally, I've got none of those. So, not surprisingly, the 0 matrix has a coordinate representation of a column of zeros. So that's t of 1, 0. This is going to be our first column in our matrix. Okay, now we go to our next basis vector. We'll take t of that. So by definition, I take that matrix and subtract its transpose. And what I get here is 0, 1, negative 1, 0. So what's this in x coordinates? I have none of these guys. I have 1 of these guys. I have negative 1 of those guys. And none of those guys. So this is now going to be the second column in my matrix. Okay, now I take t of the third basis vector. So I take the matrix minus its transpose. So that's 0, 0, 1, 0 minus 0, 1, 0, 0. That gives us 0, negative 1, 1, 0. And now I try to express this in terms of x coordinates. So I have 0 of the first basis vector, negative 1 of the second basis vector, 1 of the third basis vector, and none of the fourth basis vector. This is going to be our third column in the matrix representation of t. All right, last guy we got to check. We take t of the last one. By definition, we take the matrix minus its transpose. But just like the first basis vector, this guy's symmetric. So I get all zeros. So just as before, the matrix representation, or the coordinate representation rather, with respect to this matrix is a column of zeros, and that's our fourth basis vector. So we put all this together. Matrix representation for t. The first column is just a column of zeros. The second column is 0, 1, negative 1, 0. 0, negative 1, 1, 0. 0, 0, 0, 0. The question is how we can check it. We'll do that next.